What's your favorite movie? Like, from a physics perspective.
Interstellar.
Oh, I was literally about to ask.
So this is
I
funny.
was literally about to ask.
I have not seen this film.
Oh my goodness.
So,
You gotta be kidding me.
I haven't seen it. So I'm David has asked me this before and he's like, oh, you need to watch it. And of course I haven't.
So
yet.
there is one class that I want to design and teach at some point in my life, which is science in the movies. Physics, right? In the movies.
I'll take that class.
That
I'm not
sounds
even in college.
fun.
I'll take that.
That sounds fun.
Welcome back
Welcome, David.
to the podcast.
And again, we are behind the bar today.
Yes, which means we're joined by an honored guest,
Hey,
Dr. Feitosa.
my pleasure.
It's great to have you here. Thank you so much for coming.
I don't have a chance to go to many podcasts, so it's an honor to be here.
Fair enough. So it's not obviously like you're probably the first guest that we've had that is obviously a professor, but then also in the realm that we're going to be talking about today. I'm interested. Do you mind just sharing a little bit about your work, what you do?
Sure.
And
Yeah.
So I'm a professor of physics at James Madison University.
okay.
I've been at the Department of Physics and Astronomy for 15 years now.
Wow.
Prior to that, I was at the University of Pennsylvania as a postdoctoral researcher
Okay.
for several years, for a couple of years there, precisely 5. And then I did my doctoral studies at the University of Massachusetts Amherst.
Okay.
And my undergrad was also in physics, all of this in physics.
Okay.
I did my undergrad in Brazil at the University of São Paulo. So that's my professional trajectory.
Okay, cool. And so in that, so a professor, like what is this may sound like a silly question, but what does a professor of physics do?
Oh, that's a good question.
Yeah,
Do they all do the same
Are we
thing?
teaching? Like what are we doing?
So we obviously we teach classes.
Sure.
The classes that in the physics and astronomy department at JMU, we try to balance the classes that all of our faculty teaches. So
Sure.
I teach a couple of more advanced classes and more introductory classes. This upcoming semester, for example, I'll be doing calculus-based introductory physics
Okay.
for engineers, and I'll teach a lab class that is for science majors.
Okay.
Last semester, I was co-teaching biophysics, which is a more advanced class,
Okay.
more for seniors and majors in physics. So we try to balance lab classes with more advanced, introductory classes with more advanced ones.
Sure.
And this is the teaching part, right? But we also are involved in research, and I have a research lab.
A research lab.
Yes.
Okay.
I'm an experimentalist. My area of research is soft condensed matter physics.
Okay, wait, sorry. Can I pause you there?
Oh, absolutely.
What does all that mean?
Wait.
Yeah, okay.
So I had ChatGPT
Aha!
explain to me your research
Oh, good.
and to explain it to me as if I was a 10-year-old.
Oh,
So I would like for you to correct ChatGPT.
well, I'm no ChatGPT. Let's see if I can do better.
So according to ChatGPT, because honestly, when I read what you said, I was like, man, I wish I understood what this means. So I had ChatGPT.
So you looked up what he
I looked up what he said.
Okay,
I
okay.
looked
yeah,
up
you
what
looked
you said
okay.
in terms of soft condensed matter, right?
Yeah.
So this is explanation to a 10-year-old.
Let's
all
see.
right? So when
Let's hear.
Dr. Feitosa studies how squishy, soft, messy stuff works.
That's a
So far, so good?
pretty good start.
Okay.
Squishy, soft, messy stuff.
You know how there are hard things like rocks and soft things like slime or bubbles? Dr. Feitosa studies soft things. So they give examples, right? So like bubbles, tiny balls, stretchy sheets, liquids that act like a little bit like solids. But here it says, why does he study this stuff? Because soft things don't behave like regular solids or liquids. Sometimes they act very weird. A pile of sand can flow like a liquid, but also pile up like a mountain. Bubbles can hold shapes but pop if you touch them wrong. Thin sheets can fold or wrinkle in super complicated ways, and some powders, like in medicine, have to be just the right size and shape to work properly. Dr. Feitosa wants to understand, why do soft things behave the way they do? Can we control them to make useful stuff? And I'm losing the other part of my paper, but
I couldn't have done better.
Really?
Okay. Oh, great. Okay, fantastic.
Are you serious?
You see, I'm always scared of AI.
Okay. That's okay. That's okay.
So it is pretty accurate. It's the science of everyday things, right? Stuff that we handle regularly, like sand, bubbles, mayonnaise, ketchup. These are all part of what we call soft materials. And the word soft already gives you a hint of what they are, right? So they do not resist stresses very well, right? They break, falls, flow, and the physics that controls those behaviors are actually quite difficult to explain and understand and predict, which is the most important part, is trying to figure out, what is going to happen if I do this to this material, right? So it's a great summary of what I do, and it has impact on other areas of physics also. So there is a phenomena that we find, especially in granular materials. We call it jamming.
Okay.
Which happens when you increase the think of your salt shaker, right?
Sure.
You're trying to pour salt on your food, and all of a sudden you don't have any grains coming out anymore because they all jammed on the little holes there.
That happens to me all the time.
All the time,
so
right?
Annoying.
And it has direct implications, or applications, I should say, to other kinds of phenomena, like the jamming of 81 that happens more often than not, right?
Sure.
How do we solve that problem there, right?
Sure.
Or problems that are more complex, such as the vitreous glass. So I don't know if you've heard before, but glass is a fluid, right? The glass that we have on our windows, it's really not a solid.
Okay,
It
I didn't
looks
know that.
On the carbon?
All right.
Oh, like this window? Like
That's right, exactly. That one.
Okay, so
yeah.
that's not a explain explain to me like I'm a 10-year-old.
It feels like one.
It looks like a solid, but it flows. It has such a high viscosity that the rate of flow is, takes a long time. And when I say long, I mean thousands, hundreds of thousands, maybe millions of years.
Okay.
So to kind of wrap your head around this, think about how glass is made, right? So
Sure, it's
you
heat.
get this thing really hot, and those guys that are excellent at doing this, they take it out of the oven there, and they start shaping it. And you have to do this at a relatively fast, because otherwise it's going to harden, right?
Yeah.
So as the temperature decreases, the viscosity of that liquid, it's pretty liquid, right? When you take out of the oven, increases. So think about a type of molasses that you put on the refrigerator, and it becomes harder and harder for you to scoop it out.
Okay.
So what is happening with glass is it's the viscosity, which is the ability to flow, is it's getting higher, so making it harder and harder to flow, to a point that it takes many days, many hours, many years to flow again.
Okay.
So, now, one of the fundamental questions in physics is, if I wait long enough for the glass to flow, right? You would imagine that a panel of glass would start as a panel, right? A flat sheet. And hundreds of thousands of years later, you would be sagging and accumulating in the bottom like a liquid would do, right? The question that scientists have asked themselves is this liquid in this jammed state, right? Because it's like the molecules can't flow past each other. That's the reason why it's not flowing really well,
Okay.
right? They are all entangled kind of thing.
Sure.
So is it really a new state of matter? Like we have solids, liquids, and gases.
Yeah.
Maybe there's a fourth state of matter that we should call glassy state.
Okay.
And-
Interesting.
And my research kind of helps study that kind of phenomena. Why? Because unlike glass, which I can't see the molecules and what they are doing at the microscopic level,
Yeah.
grains of sand I can. And,
Sure.
little microscopic droplets I can take to a microscope and look what they're doing. So the jamming phenomena in these other materials could inform the physics that is behind the formation of these glassy systems. And if you think about, it's not just about manufacturing glass, right? When lava comes out of a volcano, it comes molten and it hardens and becomes
Volcanic rock,
right? So
Yeah.
it's important for geology, it's important for planet formation, it's important for many other areas of science.
Interesting.
Okay, so what would I need to know about you as a kid
Yeah.
to have any idea that this is what you'll be doing growing up?
Mm,
Is there anything from your childhood that connects to what you're doing?
Boy, no, I had no idea I would be working on this.
Okay.
I wanted to be first a doctor, then I wanted to be an architect. When I was about to go to college, I opted to, I wanted to be an engineer. But in Brazil, to get into the engineering program, it's really competitive. So I thought maybe I should go. I really liked physics. Since the very first physics class I had a wonderful professor in high school. I remember to this day arguing with him. He made that wonderful demonstration, right? That heavy and light objects, they hit the ground. If you drop them at the same time, they hit the ground at the same time.
Yeah.
And I couldn't believe that was true. And he made the demonstration in class, and I was like, what is this?
Wow.
So I really loved physics from the start.
Yeah.
And I thought before going to college, well, I can take, maybe a semester or 1 year of physics before I get into engineering. It was a lot easier to get into the physics program and I can transfer the credits.
Right.
And here I am so many years
You got
later,
sucked
never
in.
switched.
You
Never
got
did the
sucked into
switch.
the physics black
That's
hole.
right.
No
Yeah.
pun intended.
Yeah.
That's funny.
I can't escape it anymore.
Yeah. Wow. That's awesome.
So there is an event horizon. Going with the analogy, right? I mean,
okay.
if you cross that point,
It's
beyond.
done. Fair enough.
That's amazing.
Fair enough.
What's your favorite movie? Like from a physics perspective.
Interstellar.
Oh, I was literally
Okay.
about to ask.
So this is
I
funny
was
'cause
literally about to ask.
I have not seen this film.
Oh my goodness.
So,
You
yeah.
gotta
like,
be kidding,
I
dude.
haven't seen it. So I'm David has asked me this before and he's like, oh, you need to watch it. And of course I haven't.
So
yet.
there is one class that I want to design and teach at some point in my life, which is science in the movies, physics, right, in the
Ooh.
movies.
I'll
Okay.
take that class.
That
I'm not
sounds
even in college.
fun.
I'll take that. That's fine.
That sounds fun.
And the idea is really to explore the physics that you see in movies. And the name of the class should be the I forgot. Now, what was the name?
Okay, yeah.
The good, the bad, and the ugly.
There you go.
So the good science,
Yeah,
the bad
yeah,
science, and the
that's-
ugly
And
science.
and the ugly science, that's good.
Okay.
No pun intended.
So, Interstellar is pretty good in a lot of what it describes in terms of the science. One of the best parts of the movie is how some of the astronauts,
Yeah.
they age
Yes.
much slower
Yes.
as compared to people on Earth, for
Yes.
example, right? And
Dude, it's so
and
good.
it's,
Okay.
it's relative.
All right, well, then maybe
the
I'll have to-
theory of relative kind of predicts these things, so they kind of play that aspect on the movie. So that's one that I like a lot.
Nice.
Gravity is pretty good too in the science
Gravity? Okay.
side. I
Yeah,
think
yeah,
that
I haven't seen, what's
so-
Gravity? I
good.
haven't seen that. Or
It's like
heard of
what's her name? Forgetting that lady's
Um, George Clooney, I think, is part of that.
Yes,
And what is
yes.
the actress? I'm trying
I'm
to
forgetting the
remember.
actress's name.
Anyway,
but
But
it's also the movie.
Okay, well,
But
I have
Interstellar, Christopher Nolan, it's
okay. Well, if it's
undoubted.
Christopher Nolan,
Yeah.
then
Yeah.
I usually like Christopher Nolan.
he's pretty good.
but-
Yeah.
Okay, so I'm curious then. So obviously, we've gotten a 10-year-old's definition of what you study. What were some of the? Are there some recent or previous studies that you researched more specific? What were some of the research studies that you did more recently?
So I have focused a lot on the nature of jamming in my.
And you alluded to that, yeah. Okay.
Right, exactly. I actually, so it's interesting you asked about whether I thought about doing this as a little kid, and I was already when I got into grad school, I wasn't quite sure what I want to do, which area of physics I would like to research, and initially my thought was to do something related to physics educational research.
Okay.
It turns out that I switched. As soon as I got in, I switched from there to something else. There was an opportunity to do research with some astronomers doing device work, developing detectors for cosmic microwave background.
Whoa, okay. So what is that? Okay.
Yeah. So, and I'll tell you why I got interested into that part. One of the things that really fascinated me in physics was how can people get to very low temperatures, right?
How can people?
Yeah, well, we can create refrigerators, so to speak, that can get to almost 0 Kelvin. So let me unpack this a little bit.
Okay.
You cannot get something cold indefinitely cold, right, or infinitely cold. There is a limit. There is a bottom. You can get only to what we call 0 Kelvin. So Kelvin is a scale of temperature that is based on, studies of thermodynamics. And it is sort of the coldest anybody could get any molecule or material.
Yeah.
Okay.
Right?
Yeah.
So I have always been fascinated about how do people get to very low temperature, like millikelvin temperatures, which is 1,000th of a degree above the bottom. You know what I'm saying?
Wow.
So just as an example, our room temperature will be 300 Kelvin, more or less. So this is the temperature in the Kelvin scale.
Okay.
70 Fahrenheit would be equivalent to.
Okay.
And so when I was in grad school, there were some astronomers that were developing detectors for observation of what I mentioned, which is the cosmic microwave background. So this is another interesting story in physics. Several years ago, there were some scientists that were looking at the sky, and they discovered that by accident that there was some radiation that they were getting that they, no matter where they pointed at the telescope to, and those were radio telescopes, right? They couldn't get rid of it. It was like everywhere, no matter where they pointed to. And so they were kind of baffled. They initially thought that there was a problem with their instrument, tried to fix it, but eventually they realized that there is this latent radiation that permeates the entire universe. And in order to detect that radiation, you have to operate, because it's very faint. Your detector has to be at very low temperature. And you have to cool it down, because what happens is any hot surface emits radiation, right? So if you have hot surfaces around, your detector will be detecting the radiation coming from objects rather than stars or the places that you want to see out in the universe. So you have to cool down everything around your detector as the detector then receives the radiation and reads what is coming out of the cosmos, right? So this cosmic microwave background is permeates the entire universe. In fact, wherever you point, there will be this latent radiation that is coming towards us, coming from the ends of the universe, the edges of the universe, pretty much.
Yeah.
And the current understanding is that these are remnants of what might have been the Big Bang billions of years ago.
Okay.
So as the universe cooled down, that radiation, as it cools down, the radiation gets fainter, and every radiation is also, there's a temperature associated with it, right? So the color of the light that is emitted, it's related to the temperature at which that object is radiating. Wow. So the cosmic microwave background is a very cold radiation. It's at 3 degrees Kelvin. So you have to cool your detector to temperatures that are really, really low for you to be able to detect that
up.
Faint. Yeah, absolutely.
How do you cool that?
Yeah.
That's what I did in my first research. Man, this is taking a long detour. I guess. I'm so sorry.
It's okay.
I have a follow-up question.
Absolutely. So you actually have to you create a container that initially you filled up with liquid nitrogen, and liquid nitrogen. It's cold at 73 Kelvin, right? So we are at 300, you get to 73. Okay. Then you pump that liquid nitrogen out and fill it with liquid helium, which is, helium liquefies at 4 Kelvin. So we go from 300 to 73, then from 73 to 4 Kelvin. And the actual detector that I worked with was sitting on a platform that was connected with helium-3 refrigerator that got temperatures to 1, 2, 3 Kelvin.
Whoa.
Yeah. Wow. So you go into different stages cooling down the material. And I remember my days as a graduate student there, I had to babysit the experiment for several days, right? 3-4 days to get the temperature low. You cannot just jump from room temperature to those very low temperatures. You have to go on stages, cooling down the material. And to warm it up, you also have to do it slowly as well.
Wow.
And at some point, I got tired of just doing this. Like, I think this is enough. I'm probably going to try something different.
Okay.
And that's when I transitioned to soft matter, because it was benchtop experiments. I was essentially shaking sand, which was great because if you add all of the experimental data that I collected, I used a high-speed camera to take picture of grains being shaken on a container, right? So if I add all of the little videos I took during that time, it would probably add to 1.5 minutes or 2, and I did my entire PhD on that.
Wow!
Yeah,
wow!
A minute and a half.
Yeah, because it was just a second or two, and I had several of those, probably 1.5 minutes of actual
so collectively
data
like 130.
Yeah, thousands and thousands of frames because it was high-speed camera.
Okay, that makes more sense.
That's amazing.
Yeah.
You know, a lot of what you're describing is so beyond what at least what I do as a therapist, or seemingly, right? And the reason why I say seemingly is because, when I hear you describing, even just like being able to detect this very low temperatures and like referencing the radiation and the universe and all this stuff, right? I've heard, many people reference that, the study of physics and the universe and all these things brings up a lot of existential anxiety. Because like, this is so deep. This stuff is so complex. Like, this is so beyond me that it brings up, because there's so much. I think one realizes how much they don't know about the world and how things work. That it brings, that uncertainty brings up a lot of existential anxiety for them. And the reason why I parallel it to therapy is even within the emotional world. You see with clients, like, they realize life is much more complex than the black and white thinking, and that brings up a lot of
problems.
And it's interesting that you,
yeah. Anxiety.
it's interesting that you mentioned that because I literally play with sand.
I
And it seems so simple, right?
do. Right.
Yeah.
And yet it's so complex.
Yeah.
Yeah, it seems so simple, but it is so
So
complex.
how do you deal with that? How do you ground yourself, if that makes sense? How do you
Right.
make sense of that? Yeah, go ahead.
So
Do you have any follow-up?
well, yeah. So I guess it sounds like, David, you're asking to like, okay, so given the fact that you work with all of these vast, innumerable possibilities and questions,
Yeah.
how is it for you as an individual, or does that cause for you as an individual, like the fact, because it would seem that you understand way more effectively than I do how much we don't know. Like, I know we don't know a little bit, but like, we don't know a whole lot more. Because you have questions to a whole lot more than you have, and you have unanswered questions to a whole lot more things. And so I'm curious, like, does that ever come up for you? And it sounds like, David, that's kind of the question you're asking. Like, does that come up for you, and how do you ground yourself? Like, or is asking those questions fun for you, or does that not provoke anything for you?
I was actually shocked to find out that people did not have answers for stuff as simple as bubbles floating around. You know what I'm saying?
They don't have answers for that.
They don't have many of the phenomena that we study. People really don't know how to predict what the outcome is going to be, which is what I mean by answers, right?
Okay, yeah.
So that's the foundation of science is really for you to observe a phenomena and tell what is behind that and what the outcome is going to be. Right?
Sure.
So people initially looked at the stars and they realized, well, every morning the sun rises, so I will predict that the next morning it will rise again at this time, right?
Okay.
But then they got a little bit better at looking at planets doing interesting trajectories in the sky, right? And then comets and so on. So that, I think, ultimately what a scientist wants to do is to understand the nature in order to predict what is going to be the outcome. And you mentioned the anxiety. I think, the more you study, the more you realize that there are so many other things that are happening in this phenomena that I don't know or have no control of, right?
Yeah.
Variables that make the lower our predictive power, so to speak. Right.
So is that humbling for you then, or
Absolutely.
is it?
Yeah. It's very humbling. And here is the interesting thing. One thing that I learned with my mentors in science is that sometimes it's not so much about the answer as about the question. What is the question that you're going to ask? And the question has oftentimes way more value than the answers that you're going to find. If you start with the wrong question, you're probably not going to get anywhere. Right.
Yeah.
So in a field such as soft matter, which is a relatively new field and emerging, right? I can confidently say that people have difficulty asking the right question. And that is a real challenge in my field specifically, right? What is the investigation that I want to do in order to understand this phenomena? What is the underlying mechanisms that controls this behavior that I'm observing, right? And formulating a good question can lead to powerful outcomes and a good understanding of what happens. So I don't know if that makes sense to you or not.
I feel like that's the same in therapy too.
Oh no, it's 100% the same in therapy, I would say. Like asking. Well, I would say you can either structure a lot of, I would say, helpful outcomes or unhelpful outcomes predicated based on the questions that you ask.
The questions that you ask, yeah.
Right? And or in many cases, the questions that people ask themselves. For instance, why am I not good enough is a very different question than what is happening, right? And so, because one already has with it an assumption of what is happening, whereas the other carries with an openness of some investigation, curiosity, exactly. So one precludes a automatic thought, and so I would wager at a very small level that's perhaps some of the same things that happens within the sciences that you're discussing is, okay, so to what level are we actually really arriving at outcomes that matter?
Absolutely.
Okay. Wow.
And-
okay. Yeah.
And
This is so cool.
yeah.
you may ask the right question. It does not mean that it's going to be an easy path to find that answer.
No.
Right? But as you pointed out, I think the question kind of frames your approach to the problem, right?
Sure.
It provides you with a pathway to explore in a way that will be fruitful or not, whatever phenomena that you are investigating or observing.
So I'm curious, and I'm going to weave in a certain direction here. And, so this was interesting. So recently I came across, well, I guess it was recently because I think I had seen it before as well, but I had never actually thought about it very long. But I came across a research study looking at the effects of basically consciousness in water crystallization, right? Am I saying that correctly? Is that?
I think that's
Like,
right.
and- yeah. Okay. Yeah.
Don't look at me, man.
I think. Well,
I don't know.
Yeah. Fair enough. So, and I'm curious, like, so, and I had sent this to you earlier because I was curious to know some of your feedback on it. But with that, obviously, the study suggests, or rather, it was the question being asked was, okay, whether or not our conscious thoughts can have an impact on physical matter, right? Because if it can, then presumably it could have an impact on someone else's physical matter, like if we are physical beings just like other things in the rest of the world. And so effectively, I believe and again, feel free to fill in pieces here because you read over this as well, but I believe the researchers had put water in a secured lab in California, and then they had people all across the map, right? I think it was Austria, Germany, essentially think thoughts about the water, which sounds crazy because when I read this, I was like, what, really? Like,
yeah.
And then they took samples of the water and froze it and then examined what the crystals appeared to be and then rated them rated them according to beauty, I think, which it sounds like that could lead us to some different questions. But so with this, like, what are some of your initial thoughts just on that?
Well, so let me preface all of my responses with something that I tell my students in Physics 1, right?
Sure.
We teach Newtonian physics there, which is the physics that of force, acceleration, velocity, right? If you have taken a Never taken a physics class.
This is my first physics class right here.
Well, for those that have taken a physics class, that's pretty much what you learn first, right? So you learn the concept of position and then velocity, what acceleration is, and then what causes objects to accelerate. And objects accelerate because of a force, right?
Okay.
And in problems that involve force, you have to identify which object is causing a force on the other object. And there is, Newton's famous 3 laws, right? Inertia, F equals ma, right?
Okay.
That the force is mass times acceleration. And the action and reaction principle, right? That people love to quote and so on. And one of those things that I'm really, insist my students to do is you got to identify the force that is causing the acceleration on this object, right? And there are only a handful of candidates every time, right? There's either contact force, I'm physically pushing the object for it to move, or there are non-contact forces which are caused by gravity is one example, right? I'm accelerating towards the ground, even if I'm not in contact with the earth.
Sure.
Right?
Yeah.
And so the non-contact forces, there's a very limited number. It's either electromagnetic, right? Is caused by electricity that has electric field around, or is caused by gravity, which has a gravitational field that provides that mediates that interaction, right? That makes the objects accelerate or not. So I'm reading the paper. Now let's go back to the study there. And someone is trying to think thoughts towards the water, and the distance is not like I have my water here. It's like miles away.
Across the world.
Yeah, on the other side. And I'm thinking, that sounds like my student trying to do some homework. And I have to start telling my student, hey, you should think about how you're doing here.
Yeah.
Now, so I was a little bit skeptical. And it seems to be a genuine study that was performed, at least by the way that it is described in the paper.
Well, and I think it was replicated several times too.
Right.
Which it didn't yield fantastic results. But
well, part of the problem is discerning what we scientists like to say signal-to-noise ratio, right?
Okay.
So
help me understand what
that means essentially is, every measurement that we make, there are some variations there because uncertainties, right? I mean, you cannot measure anything with infinite precision.
Sure.
And if I do a measurement today and you do a measurement tomorrow and Dave does a measurement on another day, we'll always be within a certain range of some average value, right? So that's the bigger that range is, the bigger the noise is, because it's statistical noise, really, right?
Okay. Wow. Okay. Yes. Okay.
So, and when we talk about signal to noise ratio, is really, does this elevate above the statistical uncertainty that you would observe, right?
Yes.
And that's really a key point in any scientific measurement. You want that measurement to be above that noise level, that normal variation that statistic provides you. So that's one question to ask about. Sometimes the effect is so minute that you have to be really careful with your statistics, which means you probably want to take a lot of data to see if that is, you can see the same peak appearing again and again and again, even if it's a small effect. So that's one aspect to it. The other one is this idea of interaction at a distance, right?
Yeah.
So I will say two things here, right? One is, before quantum mechanics, that would be completely baloney, right?
Okay.
But quantum mechanics has given us other ways to think about the universe.
Okay, so tell me, so what is quantum mechanics?
Quantum mechanics. So, oh boy, this is becoming a physics class
Sorry,
very quickly.
This is my physics 101.
Please.
Yeah.
So there is no simple way to kind of describe what quantum mechanics is, but here is the idea, right? So at some point in the evolution of science, right, people realized there were some phenomena that was very hard to describe with Newton's laws, with the theory of electromagnetism and thermodynamics that we had classically, right? And one of the most difficult experiments to explain was what is known as the double slit experiment.
What is that?
Oh boy!
Sorry,
double slit.
Yeah, the double slit experiment. So here,
double slit.
I'm gonna. I'm gonna try to make this.
Okay.
I don't know.
I'm gonna try to make this as simple as possible with the time that we have.
Okay,
we probably
fair
have to cut a bunch of stuff. Or ask ChatGPT for more details if you want to.
Yeah.
But imagine that you are on a lake, right? And you, Dave, you are on one side of the lake, and Dave, you are on the other, and you put your foot on the lake, and you generate waves, right?
Okay.
So every time you
splashing.
you do some splashing. Every time you do this, there's a wave that forms, and the waves propagates out like this, right? So it propagates out.
Oh, okay.
So if you do on one side and you do on the other side, the waves will combine and form, areas where the crest is high when they combine constructively, or when the crest is low when they combine destructively, right? It's like, in some places will be flat because it's high on your side and low on the other one, and they kind of cancel each other out.
Yeah.
So you have those, that will be a beautiful pattern on the lake. as you look
Yes.
at it.
Yes.
Some places high, some places low, right? If only one of you is doing, you're going to have just that
Yeah.
wave propagating out. But if two people are doing, you have that pattern that forms,
Yes.
right? So people found out that you can do a similar thing with light, for example, right? You have a source of light and you put an obstacle with just two little holes we call slits, right? Two very little holes. And that was one of the ways that people discovered that light was not a particle, was an actual wave. Because when you do this, you create a pattern on the other side that looks like the same pattern that you have on the lake. So the wave patterns that form, we call interference pattern, forms on the other side of that
Slit.
Of that slit. Exactly.
Okay.
So when you look there, there will be places where there is constructive interference, where the waves from one slit add to the other one.
Okay.
Places where there's destructive, and places there is no interference at all. So that pattern is we do this experiment with our students in the lab, and you see bright points, dark points, bright points, dark points, and it looks like this, right? So that's how one of the ways that you can demonstrate that light is a wave.
Wow. Okay.
Okay, because you see the same phenomena that you see on waves in a lake. Now, it turns out that if you do the experiment with electrons, and let's say you have a source of electrons, which are thought as particles, right?
Okay.
And you put two slits on your obstacle so that the electrons can only go through those slits.
Yeah.
And you put like a
Backdrop or something.
Yeah, you have a target that can provide with phosphorus, right?
Yeah.
Let's say, so that it brights up when the electron hits it.
Okay.
You see what I'm saying?
Yeah.
So you could see the same pattern forming on the other side as light does. The same interference pattern you would form if you send electrons through those two slits.
Oh, but you shouldn't see that because they're electrons.
Well, if they are just particles, it will be just like grains of
it should
sand.
be grains and not waves.
It will be just one big bell curve, which is not the case.
Yeah. Okay.
Right? You see that.
So
you see that interference pattern, which is then that led to a real rethinking of the foundations of physics.
Okay.
And that's what we call quantum mechanics, right?
Okay.
So
Okay.
these objects, they are particles. Sometimes they behave as particles, sometimes they behave as waves.
Okay.
And the kicker really is when you try, so in order for you to see that pattern on the target, right, after it goes through those slits, you would probably have to think, even if you send one electron at a time, it seems like it forms that interference pattern, which is crazy to think, because the electron, in order to make that pattern, has to go through both slits at the same time, which is, I mean, if it's a particle, it cannot be in two places at the same time.
Yeah. Okay.
So the scientists then did something really clever. They thought, well, an electron is a charged particle, right? So maybe if I get a little device close to the slits, that when the electron goes by, tells me which slit the electron is going through.
Oh, man.
Then I would know which slit the electron went through, right? If I'm sending one electron at a time to go through these two slits to go to this phosphorus surface, right, lighting up. So here is the really crazy thing. When you try to figure out which slit the electron went through, the pattern disappears.
What?
Yes, exactly. It now becomes a regular bell curve distribution as if the electron is a particle. So you essentially destroy the interference pattern by just trying to figure out where the electron is going through.
Okay, so is
That has a lot of implications.
Yes, that's crazy.
Well, so
is that like the I guess and I'm perhaps not using this correctly, but is that like the observer effect?
The
Okay.
observer now is interfering with your experiment,
Okay.
which results in a different outcome, right?
Okay.
And this has become then a real deep discussion in physics, right? Because if I'm making a measurement and I interfere with the measurement that I'm making, what is that measurement good for? Right? I mean, it's I'm no longer.
Okay.
How do we obtain the information that we need without?
Yeah.
So the advent of the quantum physics, and by the way, this year is the year of quantum physics. This 2025
is the year of quantum physics.
Is the year of quantum
what is
physics
that- what does that mean?
celebrated?
Okay.
So the American Physical Society and many other physical societies are celebrating the year of quantum.
Well,
And
happy year of quantum.
Yeah, we are in the middle of it.
Yeah.
Okay.
And it really forced us to think different about the universe, right?
Yeah.
And I cannot go into the details of the next thing I'm going to tell you about.
Okay.
Because
At
I
least
don't
not
understand.
not on this episode. Okay.
Yeah.
Because I don't understand really all of the details of it.
Wow.
But you can, there is something in quantum physics called entanglement.
Okay.
Before I talk about entanglement, let me say something else. So if I want to send an information from one person to another, I can do this by making noise, for example, right? So let's say when it's noon here, I'm going to hit a drum set here, and you're going to hear that drum set far away, right?
Yes.
Yeah.
So noon here, boom here.
Yeah. Like
Sound
a school
takes
bell,
sound takes some time to propagate and get to where you are. If you're really far away, you're gonna get that sound a few seconds after Dale hits
Sure.
the drum here, right?
Yeah.
So what is the fastest way I can actually send information, right? So the fastest way you could do is to light.
Right.
Use light, right? Light is the fastest thing we know about. So you could light a lamp when it's noon here, so you would know far away that is, but light has its limits too, right? Even though it's super fast, it takes 8 minutes to come from the sun, which is a pretty close star. And objects that are far away takes years, hundreds of years, millions of years even to get to us, right? So for the longest time, people thought that there was no way for anybody to send information faster than light to anywhere in the universe. Then comes quantum entanglement.
Oh man. Okay.
Quantum entanglement, I can't get into the details of it because I don't understand it really well. But the gist of the issue is the following. Imagine that you particles in the quantum world, they can come into existence and out of existence all the time. But I could imagine creating a particle by radioactive decay or some other phenomena, right? That is that will eventually decay into something else, right? And if that particle is in the same quantum state, or these two particles, they are in the same quantum state. If I take them separately, and if I collapse by making a measurement on one here, presumably the other one will have to collapse into the equivalent. Let's say a positive particle, this will have to be negative because they originally were created neutral, let's say, right? So imagine that I have a particle that a system that I have two particles. I don't know what they are yet. I separate them. They are in the same quantum state. If this one collapses to be something like a positive particle, this will have to be negative, or vice versa. And it theoretically, then it's possible to send that bit of information immediately across the universe because these two objects are what we say is entangled in a quantum state that has to be, if you do something with this one, this other one has to be, the paired equivalent of that one. Now, this is as much as I can tell you.
Interesting. Okay.
It's just to let you know that it's presumably is possible to send information across long distances
immediately.
The problem is, if Dale takes one of these particles and David had the other one, if one of these collapses to be, let's say, the positive particle, Dale already knows that this one will be negative, but you don't know yet what this one was. Right?
Yes.
So you still have to send that information to Dave in order for him to know that this one is the other one. But if you do measurements simultaneously, you would know immediately that the other one is.
So you still have to figure out how to do the measurements simultaneously.
I don't know if I was able to explain well. I'm sorry, the audience, for all of the complications that this comment.
So this actually leads me to another question there, because so I'm going to chase the rabbit hole here, and maybe I'm way off base in this, because it sounds like, so circling back to that study with conscious thought on physical matter. Right. So this is really interesting to me, because presumably we talked about Newtonian law, or you talked about, I listened, right? So hopefully. And so, but this idea that, there's specific forces that can impact action reaction. But then what happens? How does physics describe or explain emotion? An emotive response.
And I don't think we can.
And so this is where I'm curious. So is that because presumably then, from a biological perspective, we might categorize emotions as chemical responses in the brain.
Right. Yeah.
Right. So, for instance, if I look at David a wrong way, right, in a negative connotation, immediately he has a neurochemical response in his body that's responding and then doing something.
Right.
Am I changing, or am I causing that? Now, from psychology, we would say, no, he gets to choose. But that's partially because of his prefrontal cortex. So if we take away and just look at things from a very basic level, right? Pavlovian perhaps. Then are we suggesting then that if he simply interprets information, I am having an impact on him only from my mind?
Oh boy!
So this is that a physics discussion? Like, I don't.
So I taught a class in biophysics, and biophysics is lovely, right? You can apply all of those principles of physics to one cell, an E. coli, for example, and try to understand all of the biological processes. And I'll tell you this: it's way more complicated than we can explain. And this is one cell, one E. coli that we explore for a whole semester, right? Imagine a living human being, which is made of, many, many, many more cells. So I like to think, and I sometimes have those thoughts, right?
It's okay. Yeah.
It's like you are just a bunch of atoms walking around, right?
Sure.
But boy, what makes those atoms want to go take, eat ice cream, let's say, right? Think about really at the most fundamental aspect of it. It's just a bunch of atoms. Why this bag of atoms all of a sudden desires to have ice cream? And why is that even good? You know what I'm saying? And it's so complex. And this is just a basic desire, right? And then you were talking about your interaction between two bags of atoms.
Exactly.
Right?
Yes.
One looks at the other, and the other is having that reaction by just the looks or the voice or the smell or something like that. And it's quite impressive that we react that way. I tell you, physics cannot offer anything really concrete. And I think that the consciousness, boy, how do you explain this at all? I really have no idea. I don't think any scientist, as far as I can tell, can really explain what consciousness is, right? What is it to be alive, to be aware of your surroundings, of all, And it is a complex thing, right? I don't think we have any explanation for this.
So then when we think about, for instance, this study of thought into, concrete, or rather, I guess we could say, just other presence, like
Physical object.
Yeah, physical object. What's your first? So would you say that you just kind of summarized your thought in that, and that we have no idea towards that, or what's some things
I
that
read
come to
that
mind?
study, and I was trying to think of ways that I could think about this. Right?
Sure.
How do I
Yeah.
how do I make sense of the study? The study essentially, in other words, people think about an object that is miles and miles away,
Yes.
and the study claims that just thinking about that object had an effect of the object, and the effect that is measured is the beauty of the ice crystals, right? So you're
Sure.
thinking about, I think that the way that the people that were thinking about the objects thought about those objects was by just looking at photographs of the objects, right? So you saw a photograph, then you think about it. And
Was it a photograph, or were they looking at a
Yeah, they
was
looked
it-
at a
was
photograph of that water.
of
of
the
that
water
water?
bottle.
Okay. Was it
Yeah.
okay? I wasn't sure if it was
A
that or a
photograph of
video
the water
stream. Okay.
bottle.
Photograph. Okay.
Which I don't think they knew about where the objects were either.
Okay.
At least that my reading of the study. So I don't want to be dogmatic about it, but I'm very skeptical of that type of interaction.
Sure. Yeah.
Just by the nature at which I've been thinking about,
Yeah.
I
get it.
Now, like everything in science, we don't have a pope, a scientific pope to say it works like this, right?
Yes.
So really, you can't pontificate what the right answer is. That's my saying.
And perhaps that's the beauty of science.
Absolutely, that's the power of science. It's the scientific method is you ask nature how nature is, right? Is that you are directing your attention in performing an experiment, and nature is telling you how things work, right? There is no authority that decides how things work. So there's only one way to really demonstrate that this is possible, is to repeat the experiment and think about a variant of the experiment and do it again. And here is another important thing to think when you think about science. A principle of science how can I explain this well? Time will tell whether or not that principle is true. There is no experiment that can definitely prove that principle that you're thinking about or talking about is true.
Yeah.
Because all you really need is a counterexample to demolish that principle.
Sure.
Right? So
is that also part of what's problematic too, in that perhaps in Newtonian physics? Is that why quantum physics became such a because you had Newtonian physics that proved counterexamples towards but then you had
so you
things...
have to think about the universe a little bit in different ways now, right?
Okay.
And so I guess the best way to illustrate this is during Newton's time, everybody thought that nobody knew what the speed of light was, right? And it was the need to measure the speed of light and figure out what that number was that led to relativity, so to speak, right? I'm not going to go into the details of how that came about, but essentially people realized that the speed of light was the same no matter the reference frame you measured, no matter where you were. If you measure the speed of light, you always get the same result. And Einstein developed his theory of relativity based on that principle. He said, well, if I take this at face value, that's what nature is telling me, right?
Yeah.
Which are the implications? And then we get Interstellar.
The
implications are if you go super fast, you age slower.
Right.
which is totally counterintuitive.
Yeah.
But why is it counterintuitive? Because nobody's going as fast as those people in that movie, right? I mean, if we were, now we can. Now we know, for example, you can have a clock on the rockets and objects that we send into space, like those probes that go to other planets, and you can easily see the difference in time passing there, right? You can measure clearly, and it's true, right?
Wow.
So it's necessary sometimes for you to then ask nature, realize that that is a principle, and then start thinking about the implications of that principle. So I think that with that experiment, I would not rule it out. I would be very skeptical, like every scientist must be, and think about other ways that I would think, well, what else could have produced that outcome?
Yeah.
Okay, and then I will think of another experiment. And if I get the same outcome, that becomes stronger and stronger and stronger. You see what I'm saying?
Yeah.
That's how science works. And someone else will try to, and the pleasure of the scientist is to disprove the fellow scientist, right? So that's how
I know, right? You guys are like
if I can
competing.
disprove, of course, that's the idea.
Makes it
If I can demonstrate that your hypothesis is wrong, well, my hypothesis is better, right? So that's how it works. So no matter how strange or different or impossible that may be, what these guys are saying on that paper is quite baffling, right?
Yeah.
I would, as a scientist, think about another experiment that would try to reproduce that result or replicate in some way, right?
Yeah.
And then I guess the next question, after you do a series of those experiments, then you start asking, how does this work?
Sure.
How can I think about something and then, interfere or change the state of that particular object? Now, having said that, I don't think we understand consciousness.
Yeah.
And because we don't, that means that there's a whole field out there that we need to explore to find out.
Yeah. So something interesting that came up for me when I was still in my counseling program, we had a module on, it's called transpersonal counseling.
Okay.
Right. And we had I even remember specifically when I opened that module and I read the word quantum physics and consciousness, right? And and there was basically there was a lot of studies on near-death experiences and basically just a lot of spiritual encounters, and basically the question is, how do you deal with that as a counselor when a client brings up these things, right?
Right.
And they were trying to allude to how science is trying to understand those things, and they brought up the quantum entanglement and is this a metaphor for spiritual connection? Thoughts, you pray or there's a spiritual thing that's travels over, like you said, faster than light. It's immediate, right? So they're saying okay, science is trying to understand these spiritual phenomenon, and as counselors we should be basically, I think the idea was that we should be open to how clients present and all that good stuff. But it's just interesting how, this field of knowledge and this field of knowledge and this field of knowledge is intersecting.
Absolutely.
Right? So I'm curious from you, right? Because it sounds like in the realm of science, like you said, physics, it's hard to explain emotion.
Right.
With physics, right? But in other realms, at least, we feel like we can understand emotion if we describe it from a psychological perspective or a neurochemical. How do you rank or rate or value different domains of knowledge in the human experience? Primarily, you're a scientist, right? But you're not just a physics professor. You're a human being. You're a husband. You're right? How do you, in your mind, make sense of how to rank, rate, and even if that, I don't know if that's the question.
Yeah. So
makes sense.
So it sounds like you're asking how do you where is your hierarchy of how you come to know something?
Yes.
How do you approach that? Is it the physics professor first? Or is it is that
so that's
yeah.
That's my
you were
I guess it's a more philosophical question.
It's a more philosophical question.
Yeah.
I come to appreciate over the years the value of different communities that practice science in different ways, or even it may not even be science per se, right? I mean, people that can show value on what they do just because of the historical experiences that have been passed on from generation to generation, right? So, which is not necessarily, sometimes we kind of glorify science in one way. This is the only way that we can learn anything. And I think that that may not be true everywhere, right? And in the spiritual realm is a good example of it, right? There are practices that help you be a better human being.
So you would say then that you believe that personally people are spiritual, or rather there's a spiritual element to
I think
the world.
I think so. I think that there is a I think it's very hard for you to think of ourselves as just a bag of atoms. This, I like to, play out this idea as a toy experiment, right? I'm going to be looking at what the implications are if I continue to do this. If I continue to think that way, what are the implications of my? And I like to think a lot about this. Think of a scenario, and then you think about what the implication is going to be, right? So let's say in the political realm, let's imagine that. I'll give one example. Since the Cold War, the United States has been the cop of the world, whatever you want to call it, right? So quenching conflicts and trying to kind of maintain the order among the nations and so on, right?
Right.
What would happen if we didn't have a United States that operated in that fashion, right? So you could play scenarios and try to think. So this is a philosophical exercise. And when I said that I like to think of myself as a bag of atoms, right? That's the most crude scientific way I could think of myself. But boy, it's so much more than just this, right?
Sure.
When I sit here with you and I talk with you, we are influencing each other. My thoughts are changing. My perspective in life is changing, right? My hopes are changing. My aspirations may be changing. How do I quantify this in physical terms? I can't. It's just, right? This is just impossible. So I have now to turn to communities that have been practicing things that clearly has an effect on people, right? So religion is one example of those communities that they, over the years, have, taught things that you should do and think and practice to improve your life and improve the way that you see things and so on and so forth. And you can think of, other communities that practice different things. They're, and not be so obtuse and think that science will answer all questions.
Okay.
So that's my. Now, we always should be careful trying to look for the outcome of all of those practices, right? Is that leading for a good outcome or not, right? Is this going to provide improvement in the quality of life, improvement on the personhood, right? So those are the ways that one could start evaluating whether those practices are good or not. I think I went on a tangent here.
No, it's okay.
That's good.
It's okay.
That's good. That's
It's
good.
okay.
Yeah.
Did you have a follow-up?
Yeah, no, that's a right, because even when you it's interesting how you talked about the bag of atoms, right? Because even that in and of itself is, we're taking that from the realm of English,
right,
and metaphor, right?
Yeah,
how do we understand? What does that mean when we think bag of atoms, right?
Right.
How does that land with somebody when they hear that?
And I should say one thing, that what is really important is not the atoms themselves, right? Because it's how they are organized. And this is an interesting thought, right? Is not so much I mean, the atoms that make me and make you and you are essentially the same atoms. I cannot distinguish one from the other. But the way that those atoms and molecules are organized make me specially unique.
Yes.
And make you specially unique and you specially unique. Is that the relative position and how they interact and, you know, how they were put together that makes you unique. Right. And that, I mean, so there is Brian Greene, a famous physicist, has a series of very nice videos about science in which he talks about teleportation. Right?
Okay.
And one way that people think about teleportation is I dismantle you here, right? But build you back with other atoms so that they are at the same position, the same relationship. We can just recreate another human, create a clone of yourself. That's what it is, right?
Interesting.
So, so it is possible. You can teleport small things like with 10, 30 atoms perhaps, but you cannot do with, you know, billions of atoms like a human being can do. But presumably the relative, the way that the atoms are organized is what is really important. It's not so much the matter that makes you.
Right, exactly. Right, and that's the thing is that you just can't separate.
Now you can disrupt the way that they are organized by influencing each other. Right? That's what a new thought, a new perspective is, right?
Okay.
Yeah.
Are we fixing the world? Are we figuring out how this works? I hope.
Yeah. I mean, go ahead.
Well, no. So I'm curious. Like, this brings to mind some other questions, just in terms of, like, because it sounds like you said earlier that like you see the purpose and value in other things outside of science. It sounds like, though, at the same time, some of those things, you brought up religion earlier. It seems like in many cases, like many scientists you hear talk about are like, I would say that it's fairly common, and hopefully I don't believe that's a generalization, but correct me if I'm wrong, but I would say it's fairly common for there not to be an association with religion or spirituality if I am a professional scientist, like if that is something that they hold truth, because am I wrong to say, like, science, like, it's the search for truth, so then anything that can't be observable is not worth then?
Oh boy, that's a big can of worms.
To unpack in 5 minutes.
Yeah, it is
in 5 minutes.
Okay, so I guess maybe let me shorten this question then. It sounds like for you came to a place to where you're like, okay, this other aspect of things is valuable,
right? So let me just say a couple of things here. Contrary to what most people think, scientists actually are not that opposed to religion, let's say, right?
Sure.
There's a lot of debate about science and religion and that kind of stuff. I don't think that's true. And part of it is because the more you learn about the universe, the more you realize that the universe is way more complex than you thought it was, right? So it is this humbling experience, I guess. And I think that now what is out there, and by out there I mean what is God and what is spirituality and all that kind of stuff, there's no clear answer that all scientists kind of believe in. Each one will probably find his or her own way of, treading that question and trying to find the answer. I do think, however, that the tools of science, they are limited to explore all there is in the universe. That's part of the problem, right? So when I do an experiment, I want to control the variables so that I can tune this one first, turn that off, tune the other one, right? And I go step by step trying to see which one causes an effect on the phenomena that I'm observing. Now, when I have 30 variables that I need to control, then it becomes difficult. So I'll give you an example, right? problems related to the effect of things that you eat, right? So I want to know if eating asparagus is good for you. Well, I cannot create an experiment. I cannot create an experiment that you only eat asparagus and nothing else. You see what I'm saying?
Yes.
So then it because there are so many other factors. And what is good for you mean really, right?
Yeah.
Exactly.
You have
mean,
to determine what that means. Yeah.
You see what I'm
Right.
saying? So the more complex the system is and the less I can control of the different variables, it becomes more difficult from the scientific point of view to solve the problem. You see what I'm saying?
Yeah.
Because other factors may be playing into this. And
Yeah.
who knows if it's really the asparagus that made you healthier,
Yeah.
whatever that means, or if it was, you slept well for several nights in a row, or you know what I'm saying?
Yeah.
Or your water was actually contaminated. Nobody knew about that and caused you to be sick. You see what I'm saying? So there are so many different ways. I once worked at a pharmaceutical company, and to develop a drug, it takes 10 years because you have to look at all of the side effects and try to figure out if that's going to, do the... So at some point, science is no longer so efficient into finding the answers, right? And that is the moment at which you have to rely on just the human experience. And I think that's what we learn from, in the culture, religion, and so on. I mean, many years, centuries and millennia, people have been trying this, and they realize that, hey, if you are nice to people, you have a better chance of survival.
Sure. Yeah.
You see what I'm saying? Or something like that.
Yeah.
So now, back to that experiment that we were talking about, right? Action at a distance, right? The ability to interfere with something at a distance. I think we scientists are a little bit skeptical, but we shouldn't be obtuse not to accept as a possibility. Because I've seen so many people praying for someone else, right? And having an effect, right? Who knows? Maybe prayer works the same way that thinking about someone, right? Maybe there is an action at a distance that we don't know. And let me give you just a little secret of many conversations I have with friends and family members about this. I always wanted to have an experiment with my students. Pray for some of them and see if they do better in school. But I never found a really ethical way of doing the experiment. Because I cannot pray for somebody.
Yeah, sure.
I will pray just for some and not for others. That would not be good, right?
Don't pray for the smart ones. Pray for the...
Can you imagine?
Yeah, right.
So you now have to start thinking about the ethical implications of how you do your experiment, right?
Yeah,
Right. And why ethic? Why bother ethics?
You
That's
see?
a complete different
A
domain
whole
of knowledge.
different,
Right?
yes, absolutely.
It is.
So the reason, obviously, as a therapist, I value psychology as a high domain, right?
Sure.
And looking back at some of the things we talked about earlier, there's this battle at least in psychology, where people are like, when, let's say, somebody has done something wrong to them and they're maybe addicted. They're strung with addiction, and this person is addicted, stole from them or something, right? There's a difficulty there to understand, like, this person clearly has a disease or something that's affecting them and their behavior, but at the same time they've done something that I cannot just excuse. So it's like, how do I balance the aspect of I'm explaining and trying to understand why they did this while not excusing it? People have a very hard time with that, because like, if you explain it, then you can excuse it.
Right.
If you excuse it, then you don't explain it, right?
Right.
And I think maybe in science sometimes there's that
Duality
of like, okay, if I can explain how if this is understandable, then does that take away, or does that add to maybe like the awe and like the unexplainable, right? Because I think we think like the divine is something unexplainable, or the spiritual, right?
In the double slit experiment, when I destroyed the interference pattern by just trying to find out which slit the electron went through, right? It's like interfering with your experiment and causing a different outcome, right?
Yeah.
So we can interfere now bring into the realm of psychology. You could interfere in the good way, and you can interfere in a bad way, right? when it comes to the spiritual, boy, I guess the philosophical question I have really is, let's assume that there is a God, right? And he will answer prayer, let's say, right? Can I really perform an experiment that will explain this really with someone that is able to make decisions independently?
Yeah.
You see what I'm saying?
Yeah, if he was a computer, you might be able to do that.
Right? I
mean,
mean,
because it was predictable. You're not dealing with...
And our own ability to make decisions is something that is profoundly difficult to explain, right?
Yeah.
Why do I do this, not that, right? We value free will. We believe we all have. Some scientists are now telling us that maybe we don't.
Yeah, right. Determinism, right?
Yeah. So, but I hope it's a problem of philosophy also, right?
Yeah.
Do we truly have free will? And if we do, what does that mean?
Right.
What is the key inside of my brain that determines that I'm going to make a decision now in one way or the other? You see what I'm saying? So I think we don't have the tools in science to explain that yet.
Yeah.
Maybe we will in the future.
Well, no, I think this is beautifully summed up though. And I guess in closing, obviously, in a good way, I think we're left with more questions than answers.
Oh, yeah.
Right? Yeah. So that's part of it. And so I think
you can continue the podcast.
Exactly. We can continue the podcast. And this has been such a good conversation. We'll have to continue it again at some other point so we can learn more about entanglement.
Oh, yeah.
Quantum entanglement.
Quantum entanglement. But Dr. Feitosa, thank you so much for coming.
It was a pleasure. I love the conversation.
Yeah, thank you.
I feel so much smarter at this.
Yeah. I don't know that I feel smarter. I just feel more like curious.
Yeah.
I'll tell you this. I don't have many chances to talk to people about physics. So it has been a wonderful opportunity, no doubt.
Thank you.
Well, thank you again. And I think that's a wrap for today. All right. Excellent.
Thank you.